2.3 Maclaurin Series. Now, many functions can be written as an infinite sum of terms of the form ax to the power of n. And you've already encountered series expansions like the first two shown over here. If we were to expand 1 over 1 minus x using the binomial expansion, you'd find we get 1 plus x squared plus x cubed, etc., where the mod of x is less than 1. And again, using the binomial expansion, if we were to expand something like the square root of 1 plus x, you'd end up with 1 plus x over 2 minus x squared over 8 plus x cubed over 16, and then we continue on. And again, the mod of x is less than 1. The Maclaurin series allows us to expand more complicated functions such as e to the power of x. And if we use the Maclaurin series to expand e to the power of x, we'd end up with 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24, etc., where x belongs to a set of real numbers. Now, the whole point of a Maclaurin series is, let's suppose you want to type into a computer e to the power of 5. What the computer is doing is using a series expansion like this and replacing the x with 5. And so if we were to work out e to the power of 5 on a computer and program it, we'd end up with 1 plus 5 squared over 2 plus 5 cubed over 6 plus 5 to the 4 over 24, etc. And in the next example, we'll take a look at the proof of a Maclaurin series. Example number 7. Given that f of x can be differentiated infinitely many times, and that it has a valid series expansion of the form f of x equals a0 plus a1x plus a2x squared plus a3 x cubed, etc. Of course, we're adding on a general term ar x to the r, and of course a0, a1, a2, a3, and in general ar are all real constants. We have to show that the series expansion must be given by this result: f of x equals f of 0 plus f dash of 0 times by x plus f double dash of 0 times x squared over 2 factorial, and then we continue this. In general, we add on the rth derivative of f at x equals 0 times x to the r divided by r factorial. So what I've written out over here is f of x, and what we need to do somehow is find out what a0 is, a1 is, a2 is, a3 is, and in general what ar is. And if you compare this result with what we have here, we somehow need to show a0 is equal to f of 0, a1 is equal to f dash of 0, a2 is equal to f double dash of 0 over 2 factorial, etc. Now, the way we can get a0 over here is by substituting x equals 0 into here. That will eliminate all these terms here, and we'll just be left with a0. So, clearly, f of 0 is equal to a0. Now, for us to find what a1 is, we need to differentiate f of x. So if we differentiate f of x, f dash of x, well, here, differentiating a0, we get 0. Differentiating a1x, we end up with a1. Differentiating a2x squared, we'll end up with 2a2x differentiating a3x cubed, we'll end up with 3a3x squared, and then we can continue this differentiating ar x to the r, we'll end up with r times by ar x to the r minus 1, and then we continue on. And for us to find out what a1 is, if we substitute x equals 0 into this result, all these terms will disappear. We're left with a1. So therefore, what you can hopefully see from here, f dash of 0, that's equal to a1. Okay? And for us to find out what a2 is, we need to differentiate f of x again. So if we do that, f double dash of x, well, if we differentiate the a1, we end up with 0, and if we differentiate the 2a2x, we'll end up with 2a2. And I'm going to rewrite this as 2, lots of 1, lots of a2. If we differentiate the 3a3x squared, we'll end up with 6a3x. And I'm going to rewrite this as 3, lots of 2, lots of 1, lots of a3, lots of x. And then we can continue on with the other terms. So if we differentiate this result over here, we'll end up with r, lots of r minus 1, lots of 1, lots of ar, lots of x to the power of r minus 2. And then of course we can continue with the other terms. And for us to find out what a2 is, again we can set x equal to 0, which will eliminate all these terms here. So f double dash of 0, that's equal to 2, lots of 1, lots of a2, and therefore a2 is equal to f double dash at x equals 0 divided by 2 times by 1. Okay? Now, for us to find out what a3 is, we would have to differentiate f double dash again, which will get us f triple dash. So, if we find out what f triple dash of x is, differentiating this we get 0, and if we differentiate the 3 times 2 times 1 times a3x, we'll end up with 3 times by 2 times by 1 times by a3. And then of course we continue, and if we differentiate this result, we'll end up with r, lots of r minus 1, lots of r minus 2, lots of 1, lots of ar times x to the power of r minus 3. And then we can continue on with this. And again, if we set x equal to 0, terms here will disappear. We'll just be left with terms involving the a3. So f triple dash of 0, that's equal to 3 times by 2 times by 1 times by a3. In conclusion, a3 is equal to f triple dash at x equals 0 divided by 3 times by 2 times by 1. Now, if we continue this way by differentiating r times, hopefully here, what you can see, if we find the nth derivative of f, hopefully here you can see we'll end up with r, lots of r minus 1, lots of r minus 2, and then we continue until we get 1, and then we times by ar. And now, for us to find out what ar is, of course, we set x equal to 0. So f r x, in other words, the nth derivative of f, at 0, that is equal to r, lots of r minus 1, lots of r minus 2, etc. up until there's 1 times by ar, and therefore ar, that's equal to the nth derivative at 0 divided by r, lots of r minus 1, lots of r minus 2, etc. and then we finish off at 1. What do you notice over here? Hopefully here you can notice this result here is the same as r factorial on the bottom, because we have r times by r minus 1 times r minus 2, etc. and we finish at 1. So here we have the nth derivative of f at 0 divided by r factorial. You can see here we get the third derivative at 0 divided by 3 factorial. Here you can see we get the second derivative at 0 divided by 2 factorial. And of course here we're dividing by 1 factorial. Here we're dividing by 0 factorial. So perhaps if we write this down, we can therefore conclude a0 is equal to f of 0 divided by 0 factorial. a1, that's equal to f dash at 0 divided by 1 factorial. So now all we need to do is substitute all these results back into what f of x is. So if we do that, what you can hopefully see here is that f of x, that's equal to a0, which we said is f0, plus a1x. Now we said a1, that's f dash of 0, and then we times this by x. And then the next term, we have f double dash at 0 divided by 2 factorial times by x squared. Next term, we have f triple dash at 0 divided by 3 factorial times x cubed. And then we continue this to the nth derivative at 0 divided by r factorial times by x to the power of r, and then we can continue on with these terms. So what we've done over here is prove the result of the Maclaurin series. Now, in this process outlined in the worked example above, that was example number 7, a polynomial in powers of x is being formed step by step. This process focuses on x equals 0. Substituting x equals 0 into successive derivatives increases the power of the polynomial. So for example, if you stop the process after finding f dash of 0, the polynomial is linear, because we've got f of 0 plus f dash of 0 times x. After f double dash 0, it is quadratic, because f of 0 plus f dash of 0 times x plus f double dash of 0 over 2 factorial times x squared is quadratic. If we stop after the third derivative at 0, you'd find that to be cubic, because f of 0 plus f dash of 0 times x plus f double dash of 0 divided 2 factorial times x squared plus f triple dash of 0 over 3 factorial times by x cubed, etc. is cubic, and we can continue this. What this assumes is that the function can be written in the given form. This is only true if the given series converges. The above reasoning also only holds if the function can be differentiated an infinite number of times and if the rth derivative of f at 0 is always finite. So let's explore this. Not all functions satisfy the condition that f of 0, f dash of 0, f double dash of 0, etc. all have finite values. So for example, if we have f of x equals the natural log of x, f dash of x is equal to 1 over x, and if we work out f dash of 0, you'd find we get 1 divided by 0. So this is undefined, and therefore this does not have a finite value. So in general, the Maclaurin series is shown by this formula here. F of x is equal to f of 0 plus f dash of 0 times x plus f double dash of 0 divided 2 factorial times x squared, etc. The general term, we've got the rth derivative of f at x equals 0 divided by r factorial times x to the r. And the series is valid provided that f of 0, f dash of 0, f double dash of 0, etc. and in general the rth derivative of f at 0 all have finite values. Now, happily for us, this is all in the formula book. So if you take a look in the formula book, you'd find over here we have the formula for the Maclaurin series, and that's shown at the top over here. And we've also got different Maclaurin series for different series. For example, we've got the Maclaurin series for e to the x, the natural log of 1 plus x, sin x, cos x, and the arctan of x. Okay? So if we take a look at what else is said over here, you can see that the polynomial f of 0 plus f dash of 0 times x is a Maclaurin polynomial of degree 1. We said before it was linear. The polynomial f of 0 plus f dash of 0 times x times f double dash of 0 divided 2 factorial times x squared, that's a polynomial of degree 2 because it's quadratic. And in general, the polynomial f of 0 plus f dash of 0 times x plus f double dash of 0 divided 2 factorial times x squared, etc. and in general going up to the rth derivative of f at 0 over r factorial times x to the r, this is the Maclaurin polynomial of degree r. And even when f of the rth derivative of f at 0 exists and is finite for all r, a Maclaurin series expansion is only valid for values of x that give rise to convergent series. So if we take a look at the Maclaurin series for 1 over 1 minus x, you'd find this to be 1 plus x squared plus x cubed, etc. Now if we substitute in x equals 2 into this result, on the right hand side we have 1 plus 2 squared plus 2 cubed, etc. So we have 1 plus 2 plus 4 plus 8. And this will not converge to the result when we substitute in x equals 2 into the left hand side, 1 over 1 minus 2, which is minus 1. And the range of validity for some individual Maclaurin series is given in the formula booklet. If no range of validity is given in this chapter, you may assume that the expansion is valid for all real values of x. Example number 8. For part A, we have to express the natural log of 1 plus x as an infinite series in ascending powers of x. Now, of course, to do this question, we need to use the Maclaurin series. And just as a reminder, here we have the Maclaurin series. We need to work out the derivatives of f of x and then substitute in x equals 0. This is the general form of a Maclaurin series. So if we apply our knowledge in this question, for part A, we begin with f of x, which is equal to the natural log of 1 plus x. And now, what you can hopefully see over here, f of 0, that will equal the natural log of 1, which is 0. If we work out what f dash of x is, differentiating a log, we have 1 over something. So here, we'll end up with 1 over 1 plus x, and then we times by the derivative of the bracket via the chain rule. So we end up with 1 over 1 plus x, which we can rewrite as 1 plus x to the power of minus 1. And if we work out f dash of 0, you'd find we get 1 plus 0 all to the power of minus 1, which is equal to 1. If we work out the next derivative, f double dash of x, you'd find here, if we differentiate this result, we'll end up with minus 1 plus x to the power of minus 2. And now if we work out f double dash of 0, you can see here we get minus and then 1 to the minus 2, so that will be minus 1. If we work out the third derivative, differentiating this result again, well, we've got the minus 1 times by the minus 2, so I'm going to rewrite this as minus 1 times by minus 2 times by 1 plus x to the power of minus 3. And if we work out f triple dash of 0, you'd find here we get minus 1 times by minus 2 times by 1, so that will be 2. And I'm going to rewrite this 2 as 2 factorial, and you'll see why in a second. If we work out the fourth derivative, of x, we will have the minus 1 times the minus 2, and then we'll have this result times by the minus 3, lots of 1 plus x to the minus 4. And if we work out what fourth derivative of f at 0 is, you'll see here we get minus 1 times minus 2 times by minus 3, which is minus 6, and then we times by the 1. So here we get minus 6, which I'm going to write as minus 3 factorial. And then hopefully here you can see, if we continue up until the rth derivative of f, well, here we'll get minus 1 times by minus 2 times by minus 3, and then we times this by, well, as you can see over here, if we think about a pattern which is emerging, you can see for the fourth derivative we had minus 3, which is 1 more than the minus 4. Now, if we take the minus over here, and if we look at what r is, you can see we have minus and then r minus 1. And hopefully you can see why this result matches up to the terms shown here. And then we multiply this by 1 plus x to the power of minus r. And that makes sense because for the third derivative we had minus 3, fourth derivative we had minus 4, etc. So now when we come to work out what the rth derivative is at 0, well here, hopefully here you can see we have minus 1 to the power of r minus 1, and that makes sense for these terms over here, and the minus 1 simply alternates the sequence, and then because we've got the 1 times 2 times 3 etc. up until the r minus 1, essentially we've got r minus 1 factorial. Okay, so now what we can do is simply substitute into the general form of a Maclaurin series, as we see over here. So therefore, what you can hopefully see from here, the natural log of 1 plus x, this is equal to f of 0, which is 0, okay? And then we've got f dash of 0, which is 1. And then we times this by x. The next term, we've got f double dash of 0, which is minus 1. So perhaps if we put all these in brackets, we've got the minus 1 times by x squared divided by 2 factorial. For the next term, you can see over here, we've got the first derivative, second derivative, so third derivative. This is 2 factorial. We then times this by x cubed, and then we divide this by 3 factorial. And then for the fourth derivative, you'd found we get minus 3 factorial. We times this by x to the 4, and then divide by 4 factorial. And then in general, you can see here, we've got the minus 1 to the power of r minus 1 times by r minus 1 factorial divided by r factorial times by x to the r, and then we continue on with the other terms. What do you notice over here? Well, hopefully here you can see, well, 0, let's just ignore that for a second, that's not going to change anything. We've got 1x, which is x, and here we've got minus 1 divided by 2 factorial, so that's just minus 1 over 2. So here we subtract off x squared over 2. Next term we're going to get a plus. 2 factorial divided by 3 factorial. Well, 3 factorial, that's the same as 3 times by 2 factorial. And the 2's factorials cancel on the top and bottom. So we end up with x cubed over 3. Next term we're going to have a minus. And then 3 factorial divided by 4 factorial. Well, 3 factorial and the 4 factorial. The 4 factorial we can rewrite as 4 times by 3 factorial. So here we have minus x to the 4 over 4. And then we continue on with this. Hopefully here you can see we've got minus 1 to the r minus 1 and r minus 1 factorial divided by r factorial. Well, r factorial we can rewrite as r times by r minus 1 factorial. So we end up here with this result times by x to the power of r divided by r. and then we continue on with the series. So that's how we approach part A. For part B of the question, only using the first three terms of the series in part A, we have to find estimates for the natural log of 1.05, the natural log of 1.25, and then the natural log of 1.8. And then we have to comment on the accuracy of these estimates. Now, the further away a value is from x equals 0, the less accurate the approximation will be, and the more terms of the series you need to take to maintain a required degree of accuracy. And that's because the Maclaurin series estimates around x equals 0. Now, if we consider the first three terms of the series we found in part A, we have the following. We have the natural log of 1 plus x, which is equal to x minus x squared over 2 plus x cubed over 3. Now, if we work out the natural log of, for the first part, 1.05, clearly you can see if we compare the 1 plus x with the 1.05, of course x is equal to 0.05. So this is equal to 0.05 minus 0.05 squared over 2 plus 0.05 cubed over 3. So if we work all of this out, of course we can use our calculator to work this out. We have 0.05, and then this answer, we subtract off this answer squared, and then divide by 2. And then here we add on this answer cubed, and then we divide by 3. So you'd find here, if we work all of this out to 5 decimal places, you'd find we get 0.0487916, etc. Okay, and you can see if we actually work out the value of, well, let's just write out the full thing. So we've got 916 6 6 6 7. If we actually work out the value of the natural log of 1.05, you'd find we get this value over here. So if we compare this value with what we have over here, you can see this is correct to 5 decimal places. So let's just write this down. This is correct to 5 decimal places. If we now work out using the series the natural log of 1.25, if we compare the 1 plus x with the 1.25, clearly x is equal to 0.25. So here we get 0.25 minus 0.25 squared divided by 2 plus 0.25 cubed divided by 3. So if we work all of this out, we've got the 0.25 already, and then we subtract off this squared, divide 2, plus this cubed divided by 3. You'd find if we write down all the values that our calculator displays, we get 0.2239 583333. And if we work out the actual value of the natural log of 1.25, you'd find over here this result is correct to 2 decimal places, because then after that the answer is different. So this is correct to 2 decimal places. And finally, if we work out the natural log of 1.8, clearly x is equal to 0.8. So here we get 0.8 minus 0.8 squared divided by 2 plus 0.8 cubed over 3. So if we work this out, we have this answer minus this answer squared divided by 2, and then we add on this answer cubed over 3. So it turns out here we get 0.6506666667. And if we work out the actual value of the natural log of 1.8, you'd find we get this value over here. So this is not correct to even one decimal place. So therefore, not correct to one decimal place. So to make this more accurate, of course, we'll need much more terms than this. And that's because the value of x we're choosing is not very close to 0. You can see the further away from 0 we are, the less accurate is our answer. So therefore, we would need more terms. So let's just write that down. So therefore, the further away a value is from x equals 0, the less accurate the approximation will be, and so you would need more terms of the series to maintain a required degree of accuracy. Example number 9. For part A, we have to find the first 4 terms in the Maclaurin series of sine x. So for part A, we begin with f of x, which is equal to sine x, and therefore f of 0, that's equal to the sine of 0, which is equal to 0. Now, if you pay attention to what was mentioned before regarding the Maclaurin series, we had the formula as stated over here. Now, what you can see over here is f of 0, that's equal to 0. So essentially, we can't just go up to x to the 3 in the Maclaurin series because f of 0 is 0. So let's just play around with it and see what we get. Next, we've got f dash of x, which is equal to cos x. And therefore, f dash of 0, that's equal to the cosine of 0, which is 1. So we can include this term here. If we work out f double dash of x, we'd get differentiating cos, we get minus sine x, and therefore f double dash of 0, that's equal to minus sine of 0, which is equal to 0. So we can't include the x squared term. If we work out f triple dash of x, differentiating minus sine, you'd find we get minus cos x, and therefore f triple dash of 0, that's equal to minus cos of 0, which is equal to minus 1. Now, we can include the x cubed term, that's perfectly fine. If we now work out the fourth derivative, differentiating minus cos, you'd find we get positive sine. And if we work out the fourth derivative at 0, we get the sine of 0, which is equal to 0. So we can't include x to the 4. So we've got here 1 term, 2 terms. Let's see what happens if we work out the fifth derivative of x. If we differentiate sine, we get cos. And therefore, if we work out the fifth derivative at 0, we get cos of 0, which is 1. So we can include the x to the 5 terms. So far we've got 1, 2, 3 terms. So now we need to see what we get when we work out the sixth derivative of x. Differentiating cos, we end up with minus sine x, and therefore the sixth derivative at 0 will equal minus sine of 0, which is 0. And now if we work out the seventh derivative of x, you'd find the seventh derivative is equal to minus cos x, and therefore the seventh derivative at 0 is equal to minus cos of 0, which is minus 1. So we've got 1, 2, 3, 4 terms here. And what you'll also notice, if the nth derivative of f is equal to 0, if n is even, then we've got a cycle with values 0, 1, 0, minus 1. Okay, so now if we substitute back into the general form of the Maclaurin series, we can see that sine x, that's equal to x minus 1 over 3 factorial times x cubed. And then we've got plus 1 over 5 factorial times x to the 5. And then we've got minus 1 over 7 factorial times x to the 7. And if we continue this, you can see we'll have minus 1 to the power of r. That ensures we get the plus minus. And then we divide this by, well, if you look at the 3, the 5, the 7, that forms a linear sequence of the form 2r plus 1. So here we've got 2r plus 1, and don't forget, we take the factorial of this, as we see in the other terms, and then we times this by x to the power of 2r plus 1, because the 3, the 5, the 7, etc. are of the form 2r plus 1. And then we can continue this. So if we take a look at the first 4 terms, the first 4 terms are shown over here. So here we have the first 4 terms. Okay, now for part B, we have to use the first 2 terms of the series to find an approximation for sine of 10 degrees. Now, first of all, we need to convert the 10 degrees into radians. So for part B, 10 degrees in radians, well, 180 degrees is pi radians, so 10 degrees will be pi over 18. Okay, so therefore we're working out the sine of pi over 18, which is the same as sine 10. So here, if we substitute into the first 4 terms rather the first 2 terms, we've got pi over 18 minus 1 over 3 factorial times by pi over 18 cubed. Okay, so if we work all of this out on our calculator, we type in the pi over 18. So we've got this minus 1 over 6 times by this to the power of 3. You'd find here we get 0.173646829. Okay, and if we actually work out what the sine of pi over 18 is, you'd find we get this value over here. And if you compare this with this, you can see here, this estimate is correct. Let's just write this down. This is correct to 5 decimal places. Okay, so that's how we approach Maclaurin series problems.